Hello everybody, welcome to this video looking at absolute and conditional convergence. So these are both types of convergences. If either one applies, then the series will converge, but they behave a little bit differently, so we need to be aware of the differences. And very roughly, absolute convergence means that the series converges in absolute value, so we don't need signs or cancellations or anything to make it converge. It just converges kind of by brute force, going to zero fast enough. And conditional convergence is what happens when it converges with signs but not without signs. So here somehow we are using the cancellations to make it converge. Okay, so let's see a little bit more precisely. We said that a series sum of an is absolutely convergent if the sum of the absolute values of an converges. So the series where we get rid of the minus signs, we just make all the terms positive if that series converges. And this can be useful to check instead. For instance, a lot of the results that we've seen so far are only for series with positive terms. So if we have a series that has, maybe sometimes positive, maybe sometimes negative terms, then one way is to just get rid of the negative terms, look at the sum of the absolute value of an, and use some of the previous rules we talked about. So what are some examples of absolutely convergent series rather? For instance, consider the sum of -1 to the n minus 1 over n squared. So this starts with 1 over 1 squared minus 1 over 2 squared plus 1 over 3 squared minus 1 over 4 squared and so on. Okay, and if we were to take the absolute values of an, we would get 1 over n squared. And we know that the sum of 1 over n squared converges, so that is saying the sum of the absolute values of an is converging. Okay, so this is a absolutely convergent series. Why do we care about absolute convergence? Why is it useful? Well, if the sum converges absolutely, then it is also convergent. So if we take the absolute values and what we get, the series converges, then the original series has to converge. So this can be one way of simplifying series and showing that a series converges by checking instead that it's absolutely convergent. Why is this true? A quick proof. Well, it's based on comparison test, but we can only use comparison test for positive terms. So there is a little trick. If we look at an plus the absolute value of an, this will always be non-negative, because if an is positive, the absolute value that we're adding cancels out the negative part. And it's always less than 2 absolute value of an, just because an is less than the absolute value of an. And since the sum of an is absolutely convergent, that says by definition that the sum of the absolute value of an is convergent. So the sum on the right, if we sum the right-hand side, this will be convergent. So by the comparison test with positive terms, the sum of an plus absolute value of an will be convergent. And then we were interested in the sum of an. We know that the sum of an plus absolute value an is convergent. We know that the sum of absolute value of an is convergent by the absolute convergence. So we just subtract them. We see that the sum of an is convergent. The difference of two convergent series is convergent. And it seems kind of weird. The only reason that we looked at an plus absolute value of an is to make everything positive so that we can use the comparison test. Anyway, getting back to basics, we said that if a series is absolutely convergent, then it's convergent in the usual sense. So the series we just talked about on the previous slide that we said is absolutely convergent. Of course, this is convergent by the theorem, but we also know that from before, right? By the alternating series test, for instance. Okay. However, absolute convergence is stronger than convergence. So if we look at a slightly different series, the sum of -1 to the n minus 1 divided by n. So here we're dividing by n rather than dividing by n squared. If we take the absolute values, we get 1 over n. And we know the sum of 1 over n diverges. So this series is not absolutely convergent. However, it is convergent because if we were to look at -1 to the n minus 1 divided by n, it's an alternating series, and the positive part is 1 over n, which is decreasing and goes to 0. So it's not absolutely convergent, but the series itself is convergent. So absolute convergence is strictly stronger. If it's absolutely convergent, that implies convergent, but that's, if it's not absolutely convergent, that doesn't say anything. So we have a name for these things. If the original series is convergent, but it's not absolutely convergent, we call them conditionally convergent. So it's conditionally convergent if convergent, but not absolutely convergent. So this example, the sum of -1 to the n minus 1 divided by n, would be an example of a conditionally convergent series, right? The series itself is converging, but if we look at the sum of the absolute values, we get sum of 1 over n, which is diverging. So the original series converges, it's not absolutely convergent. Okay, by definition, that's conditionally convergent. Okay, what is another useful application of absolute convergence is, if we have chaotic signs, like on the previous examples, you could argue, well, we could have just used alternating series test. But if you have something, say, a bit more chaotic, like sine of n divided by n squared, sine of 1, sine of 2, sine of 3, they're not really easy values to understand. So you can't really say that it's alternating. What could we do? For instance, if we look at the absolute value, we have the absolute value of sine n over n squared. That's positive, and it's less than or equal to 1 over n squared just by using sine is less than or equal to 1. So here we have a series which is sum of absolute value sine n divided by n squared, it's positive, and it's less than 1 over n squared, we know that the sum of 1 over n squared converges. Okay, so by the comparison test, remember the comparison test needed positive terms. By the comparison test, the series that we started with is absolutely convergent because we're saying the sum of the absolute values will be convergent by comparison test. So it can be useful even for series that are not alternating series. Okay, another important consequence, maybe we're not going to dig into this too much, but something we really need to be aware of is the absolutely convergent series and conditionally convergent series behave quite differently with rearrangements. So a rearrangement of a series is just another series that has the same terms but in a different order. So if we were to look at, alternating harmonic series, 1 minus a half plus a third minus a quarter plus a fifth minus a sixth and so on, we could add the same terms but in a different order. So rather than in the usual way, it's one positive term followed by one negative term. We could do two positive terms followed by the next negative term and two positive terms followed by the next negative term. We would still be adding all the same terms, but they would be in a different order. So this is what is meant by a rearrangement. And there is this kind of brain-bending fact called the Riemann rearrangement theorem that says if a series is conditionally convergent, then there's a rearrangement that will make it converge to any number you like. So if you pick a number, you can find a way to add the terms in a different order so that the sum is equal to R. And kind of what is going on here, we're not going to prove this because it would take quite a while, but what is going on is being conditionally convergent, remember that if we take away the negative signs, if we just sum the positive pieces, then it would go to infinity because the sum of the absolute values isn't converging. So if we were just to sum the positive parts, it will go to infinity. If we are just to sum the negative parts, it will go to negative infinity. So if we want to make it big, we could just sum a lot of positive pieces first. If we want to make it small, we could sum a lot of the negative pieces first. If we wanted to converge to anywhere we like, we just decide how many positive pieces to sum until we're a little bit bigger. Then we sum a lot of negative pieces until we're a little bit smaller, and so on and so on. So we keep playing the game in terms of how many positive pieces we pick and how many negative pieces we pick. Anyway, that's the idea. So conditionally convergent series, you can rearrange it to any number you like. And on the other hand, if we have an absolutely convergent series, every rearrangement will converge to the same value. So absolutely convergent series are much more stable. If you add the terms in a different order, you will get the same number, which is not true with conditionally convergent series. Of course, this is kind of weird because, in our experience with finite sums, it doesn't matter which way you add them, of course. Okay, just as an example, we said a couple of slides ago, the sum of negative 1 to the n divided by square root n is conditionally convergent. Okay, so you could, in this order, we don't know in the original order, we don't know what it converges to, but you could rearrange it in a different order so that it will converge to 1, or there is a different rearrangement that it converges to square root 2, or there is a different rearrangement where it converges to pi. So any number you want to make it converge to, there is a rearrangement so that you might need lots of different rearrangements for lots of different numbers that makes it converge to that. On the other hand, we said the sum of negative 1 to the n divided by n squared is absolutely convergent. Okay, whatever you rearrange it to, you're always going to get the same value. Okay, so just to summarize from this video, we looked at absolute convergence, which is when the sum of the absolute value of a n converges. That implies regular convergence. And we also looked at conditional convergence. That's when it converges, but the sum of the absolute values diverges. And we said they're quite different with rearrangements. Okay, thanks everyone. See you next time.